Okay, hello everyone. In a new video, so we have reached part 4 of chapter 5, which is the chapter of kinematics for grade 11 students. So now recall that you are in section number 2, and the title of this section is given by motion in 2 dimensions. So recall that the first subsection of this section was given by 2.1, the trajectory, and section 2.2, which is supposed to be explained now, is given by URM and UVRM in 2 dimension. Okay, so before I get into the subsection 2.2, let me recall the following. So if the motion is said to be URM, then the equations of motion are given by x is equal to vt plus x0, in which v is equal to a constant and the acceleration is 0. These equations are for the URM, whereas for the UVRM, the equations are given by, so if we start by x, it's given by half at square plus v0t plus x0, v is equal to at plus v0, and the acceleration is equal to constant. And another equation that we can add to this list is given by that v square final minus v square initial is equal to 2 times the acceleration times the displacement or the distance d. Okay, so now, so let me start by the subsection 2.2, which is given by URM and UVRM in 2 dimension. So for this reason, suppose here we have a position vector r. Since the motion occurs in 2 dimension, then the position vector r is expressed as follows: xi plus yj, in which x represents the position along the x-axis and y represents the position along the y-axis. So, okay, x is equal to x of t is given by the parametric equation along the x-axis, and y is equal to y of t is the parametric equation along the y-axis. Okay, so let's consider the following example. Okay, so before I consider this example, let me list the possible types of motion that we have. So here in this case, according to the equations of x and y, we can classify the motion of the moving particle, which is considered, for example, to be m. So x may be either URM or UVRM, and y may be URM or UVRM. So we have 4 possible motions, and they are given by along the x-axis URM, along the y-axis URM, along the x-axis URM, along the y-axis UVRM, along the x-axis UVRM, along the y-axis URM, and along the x-axis UVRM and along the y-axis UVRM. So let me list the possible types of motion. So if you consider the first case, URM along the x and URM along the y. So the second case, URM along the x, whereas UVRM along the y. Third case is that UVRM along the x and URM along the y. And the fourth case and the final case is given by UVRM along the x and UVRM along the y. Okay, so let me in this case consider the following example. Suppose that the position vector r is given by, say for example, t square plus 1 multiplied by the unit vector I plus 3t multiplied by the unit vector j. So in this case now we can determine the parametric equations that are given by x is equal to t square plus 1 and y is equal to 3t, because this represents the x and this represents the y, and for sure we can find the trajectory in this case. But now what's more important is to identify the nature of motion along each axis. So notice that here in this case, because the quadratic term appears in x, and here if you compare between URM and UVRM, so notice that, okay, first let me consider the motion along the x-axis in order not to make any confusion. So the motion along the x-axis is described by the parametric equation, which is given by x is equal to t squared plus 1. So now what's the type of motion along the x-axis? Notice that here the quadratic term appears. Now if we compare both equations, the quadratic term in the position correspond for UVRM. So in this case it is UVRM along the x-axis. Now as for the motion along the y-axis, this motion along the y-axis is eventually described by the parametric equation y is equal to 3t. So notice now in the case where the position y is linear in time, so here notice that I have labeled these quantities by x, but they are the same for y. So notice that whenever the position is linear in time, this means that the motion, so this is linear in time, then the motion is what? URM. So URM along the y-axis. Okay, so in this case, if we are UVRM along the x-axis and URM along the y-axis, then we are in the third case. Okay, but now how do we deal with this type of problem? So let's say suppose, okay, of a moving particle M, so we have the position vector r of a moving particle. Suppose r of a moving particle is given such that we have URM along the x-axis. So, or let me consider the general case UVRM along the x-axis and UVRM along the y-axis. Okay, so we have r is equal to xi plus yg. Okay, so let's start by along the x-axis. Okay, so notice now that along the x-axis the type of motion is UVRM, and the UVRM equations are given by x is equal to half at squared plus v0t plus x0, etc. Okay, so because along the x-axis the type of motion is UVRM, let me list the equations here. Then x is equal to half at squared plus v0t plus x0, v is equal to at plus v0, a is equal to a constant, and we have that v square final minus v square initial is equal to 2ad. Now in this case, this equation in 2 dimension is not of paramount importance. Okay, so now let's consider only these three. Now as for the y-axis, so the type of motion along the y-axis is given by UVRM, and we know that the equations of UVRM are given by these, which are exactly these. But now here, because we are considering the y-axis, let's change the label x to be y. So here we have y is equal to half at squared plus v0t plus, instead of writing x0, we will write y0. Now as for the velocity, it will be the same. V is equal, or the speed, at plus v0, and the acceleration a is equal to constant. But now the point that I'm going to explain is very crucial in a sense. Now notice that when comparing these equations together, the acceleration and the speed or the velocity appears both in x and in y. But nobody told us that x and y are equal in a sense. If x is different than y, and this is the general case, then we expect that the speed along the x-axis is different than the speed along the y-axis. And because x is different than y, I repeat, the speed along the x-axis is different than the speed along the y-axis, therefore also the acceleration along the x-axis is different than the acceleration along the y-axis. And this is trivial, because along each axis we may have a different type of motion. So in order to distinguish this acceleration that appears here in these equations, in order to distinguish this acceleration with this acceleration, we will label this acceleration to be the acceleration along the x-axis. Okay, why we are labeling this acceleration to be the acceleration along the x-axis? Because it appears in the equations of motions related to the x direction. Similarly here, we will label these quantities, the acceleration, by the label y. Okay, so here let me say it's a constant, and this is constant prime, another constant. They are not equal. Okay, so we are done with the acceleration, but now we still have the speed. So as I have mentioned, the speed along the x-axis may be different than that of the speed along the y-axis. So everything here that includes the speed will carry the label x. So this velocity v0 will carry the label x, as well as for this, as well as for this. Similarly here, in order to distinguish this speed from that speed, we will label it by the component y. Now as for time in classical mechanics doesn't carry any label. Okay, so always time is absolute. It's the same for the x-axis and for the y-axis. Okay, now the same steps that we have done here, we could have done for all the 4 cases that are listed here. Okay, but now what's more important is to know how to deal with these equations in an exercise. So let's consider also, okay, let me consider exercise number 13. So we have reached exercise number 13. Suppose in this exercise, so we are in exercise number 13. Okay, before I move to this exercise, I have forgot to say the following also. Then now, after we have determined the equations of motion along the x-axis and the y-axis, after specifying the type of motion, now we can say what about the speed? So okay, so the position vector r is given by xi plus yj. The velocity vector, which is the instantaneous velocity, now in this case is given by vx multiplied by I plus vy multiplied by j. And the acceleration vector a is given by axi plus ayj. Now in this case, if you are interested in determining the magnitude of the velocity, which is the speed, then v in this case is given by square root of v of x square plus v of y square. And the acceleration in this case, the magnitude of the acceleration is given by the square root of ax square plus ay square. Okay, notice that we didn't discuss these equations in the case of one dimension, because whenever we are moving in one dimension, no need to distinguish between x and y. Okay, now if you consider exercise number 13, so suppose that the position vector r is given by 3t multiplied by the unit vector I plus, say for example, 2t square plus 5t multiplied by the unit vector j. So let's say that part 1 of this exercise is given by list the parametric equations. Now number 2, determine the trajectory. Number 3, specify the type of motion, or let me write 3.1. Specify the type of motion along the x-axis. Then say for example 3.2, list the equations of motion Now 4.1, specify the type of motion along the y-axis. In 4.2, list the equations of motion along the y-axis. Part 5, determine the velocity vector v as function of time. Then deduce the speed as function of time. Now part 6, let's say determine the acceleration vector. As function of time. Deduce the magnitude. Okay, so the magnitude of the velocity is usually referred to as the speed, but we don't have anything to refer to the magnitude of the acceleration. Then let's say deduce the magnitude of the acceleration. As function of time. So basically these are all the possible questions in the case of two-dimensional motion. Okay, two-dimensional motion. Now let me start by part 1. Then given the position vector, which is given by r is equal to 3ti plus 2t squared plus 5tj, we are asked about the parametric equation. So this is straightforward. Now x, in this case, x of t is equal to 3t and y is equal to 2t squared plus 5t. Now in number 2, they are asking me to determine the trajectory, and this can be done by extracting t from the linear term and replacing it in the quadratic. So recall that the trajectory is the equation that relates x and y. Now replace t is equal to x divided by 3 and y. Then y is equal to 2 x over 3 to the power 2 plus 5 multiplied by x divided by 3, and in this case this is a parabola. Now in 3.1, they are telling me specify the type of motion along the x-axis. In order to specify the type of motion along the x-axis, we need to refer the parametric equation or the x component, which is given by x is equal to 3t. Now notice that since x is equal to 3t verifies the general form x is equal to vt plus x0, then the type of motion along the x-axis is URM. And because here the motion occurs in 2 dimensions, and in order to distinguish between the x and the y components regarding position, speed, and acceleration, let's give this v a label x. So the type of motion along the x-axis is URM simply because it's linear in time. Okay. Now, in number 3.2, they are telling me to list the equations of motion along the x-axis, and here let me write between brackets. I'm talking about the acceleration and the speed, okay, as function of time. So let's say since the type of motion is URM, okay, before saying so, okay, is URM along the x-axis. Then the equations of motion regarding the speed and acceleration are given by v is equal to constant and x is equal acceleration is equal to 0. Now because we are talking about the x component, let's give them the label x. So we need to determine the value of the constant, so the acceleration is 0 already solved. Knowing that x is equal to vx t plus x0, and in this case x is equal to 3t. So comparing both equations, we get that Vx is equal to 3, so everything in the side is 3 meters per second. Okay, so here this is given by 3 meters per second. So the equations of motion along the x-axis are given by Vx is equal to 3 meters per second and the acceleration is equal to 0. So this is it for part 3.2. Now in 4.1 we need to do the same but for the y component. They are telling me specify the type of motion along the y-axis, and this can be done by referring to the parametric equation along the y component, which is given by 2t squared plus 5t. So since y is equal to 2t squared plus 5t verifies the general form. So this is quadratic in time, so we have that y is equal to half at squared plus v0t Now here, because we are talking about the y component, let's give all the quantities the label y. Since it verifies the general form y is equal to half at squared plus v0y t plus y0, then the type of motion is uvrm along the y-axis. Then the type of motion is uvrm. Now if we refer to 4.2, they are asking me to determine or list the equations of motions along the y-axis. So we need to list a of x and v of x. Here v of x is for sure as function of time. And now let's say, since the type of motion along the y-axis is uvrm, then what are the uvrm equations? They are given by, so here, okay, we already have the position y, we need to write the velocity and the acceleration. So the velocity is given by at plus v0 and the acceleration is constant. Now let's label them by y. Okay, so we need to determine a of y, v of 0. Now because we have that y is equal to 2t squared plus 5t and the general form is given by half a yt squared plus v0 yt plus y0, then by comparison so if half ay is equal to 2, then ay is equal to 4 meters per second squared. As for the velocity along the y-axis is given by 5 meters per second. So in this case the equations are given by vy is equal to 4t plus, so this carries the label y, okay, plus 5. As for the acceleration along the y-axis is given by 4. Okay. And now finally in part 5 they are telling me to determine the velocity vector v. The velocity vector v is by definition v is equal to vxi plus vyj. Now in order to determine v we need to determine vx and vy separately, and we have done this. So vx is determined by referring to the motion along the x-axis, and in this case it's given by 3 meters per second. It's independent of the time because the motion is constant, is urm. Then this is equal to 3 multiplied by the unit vector I plus, now as for Vy, we refer to the motion along the y-axis, which is given by 4t plus 5 multiplied by the unit vector g. So the velocity vector as function of time, so here we can say v of t is equal to 3i plus 4t plus 5 j. Now in the same part they are telling me to deduce the speed as function of time, and deduce means that we notice the previous part. In the previous part we have determined the velocity vector. Now the speed is the magnitude of the velocity, so v is equal to square root of v of x square plus v of y square. Now the x component of the speed is given by 3, so 3 to the power 2, and as for the y component is given by 4t plus 5 to the power 2, and you can expand and reduce the expression under the square root. Okay, so it's given by 3 square plus 4t plus 5 to the power 2. Now as for part 6, they are telling me to determine the acceleration vector a as function of time, and this is determined by identifying the x component and the y component and of the acceleration. Referring to the motion along the x-axis, we can see that the acceleration is 0 because the type of motion is urm. So this is 0 multiplied by the unit vector I. As for the y component, the acceleration is given by the value of 4. So notice this must have a unit 4 meters per second square. So plus 4j. Although they are telling me to determine the acceleration as function of time, but here as you can notice that acceleration is independent of time, but this is okay. So the acceleration vector is given by 4 multiplied by the unit vector g. Now finally in the same part they are telling me to deduce the magnitude of the acceleration as function of time, and by deduce it means that we notice the previous part. In the previous part you have determined the acceleration vector. The magnitude is simply given by a is equal to square root of ax square plus ay square. Now so because the x component is absent, so this is 0, so it's equal to square root of ay square, which is equal to ay, which is simply equal to 4 meters per second square. Then a is equal to 4 meters per second square. So that's it for me in this video, guys. In the next part we'll solve exercises on this chapter.